Day 64 notes, Advanced Algebra 2. Today we're getting back into the algebra with polynomials, less about the graphing of polynomials, but more about the actual math and the algebra techniques that we use with them. There's a new method that I'd like to introduce at the end of this video called the table method that allows us to multiply rather large polynomials, polynomials that are trinomials and larger. But before we get to that, let's consider or remind ourselves how we would do example 1 here. Example 1 asks us to multiply each of these monomials by another polynomial. And hopefully you would recognize that the method that we use for these is to distribute. So I'm going to distribute this term to each term on the inside of the parentheses. And what I'm left with would become a 3x to the 5th power plus 12 x squared for this first example. For the next example, even though we have multiple variables, we can still distribute. So AB multiplies by this term, and by this term here. When I multiply this first term, only the a's can combine as far as increasing their exponent. So AB times a cubed would result in a to the 4th times b, plus, now for this middle term, 3a squared b to the 3rd. Again, we're combining the a's with the a's and the b's with the b's when it comes to multiplication. And lastly, we end with a negative ab to the 4th power. If you're not sure how I got these solutions, or if you weren't following along, if it didn't make sense how I got these results, please be sure to ask a question when class starts tomorrow. Now, example 2 reminds us that we can multiply a binomial by another binomial if we use the FOIL method. This is traditionally the method that we use for these types of products. So the FOIL method says find the first, the outside, the inside, and the last products. So for the first product, we have x squared times 2x, and that's 2x cubed. For the outside, we get x squared times negative 3, so that's a negative 3x squared. For the inside, we have 2 times 2x, 4x. And for the last, we have 2 times negative 3, which is a negative 6. These two middle terms can combine into like terms, and when I rewrite the result of each of these 4 steps, we see that we have 2x cubed plus x squared. Whoops. Let me back that up here. These two middle terms actually are not alike, so we cannot combine them. That's a bit unusual, but not all that uncommon. Negative 3x squared would be the second result, plus 4x and a minus 6. So the result of this product is going to be a 4-term polynomial, so a cubic polynomial. I'd like to show that multiplication again using this new method called the table method. That's going to make the examples down below a little bit easier to work with. So what we need to do to multiply using the table method is pick one of the polynomials that you want to multiply and list all of its terms along a top row. So I'll just call this x squared and 2. I'm just going to leave some space here. Then I'll pick the other polynomial and list it down as a different column. So this would be 2x and a negative 3. What the table method tells us is that I can multiply each row by each column, kind of like we would complete a multiplication table, and then combine like terms at the end to see my result. So here in this first entry, what I'd like to do is multiply x squared times 2x. That leaves me with 2x cubed. And in this second entry, I have 2x times 2. That's our 4x. For this third entry, I have x squared times negative 3. There's my negative 3x squared. And lastly, negative 3 times 2 is the value that we'll place here. negative 6. And with all 4 of these boxes completed, we can then write our final answer. And we'll collect like terms along the way, although there aren't any this time. So there's 2x cubed minus 3x squared plus 4x minus 6. And this result matches the result that we got before, which is good. And it goes to show that either method is appropriate. Now let me quickly explain why this is going to work for us. The FOIL process that we introduced back here is really just a technique, right? This FOIL acronym is a technique that reminds us that every item in this first polynomial has to be multiplied by every item in the second polynomial. Now, since these are binomials, it's relatively easy to complete that task. First times first number times the last number, so that would be our outside description. Then our second number in here multiplies by the first, and our second number in here multiplies by the last. So this acronym, FOIL, does a really nice job of reminding us to multiply each of the 4 possible terms. However, when we get into larger polynomials, that technique doesn't always work because we have more than 4 terms to multiply. In this case, we're going to end up with a result of 6, because everything from this first polynomial, each of these 2 numbers, has to multiply by each of these 3 numbers in the second trinomial. Additionally, what's a bit unusual about this one is that this is not in standard form. But that's no problem. When we use the table method, we can multiply these 2 together using the same process. So the first thing that we have to do is rewrite one of these polynomials as a column along the top of a table. So I'm going to write this as a and negative 3. Then I'll write the second polynomial as a new column down the left-hand side. So this is a 2, negative 5a, and a squared. And then from here, I'll just fill in the rest of the table. In this first column, first row, I need to multiply a times 2. That's 2a. 2 times negative 3, which is negative 6. First entry, second row, would be a times negative 5a. So a times negative 5a is negative 5a squared. Then negative 5a times negative 3, well, that's 15a, positive, because negative times another negative is positive. Then a squared times a, that leaves us with a cubed. And lastly, a squared times negative 3, that's a negative 3a squared. So when it comes down to identifying the final result, and I'll go ahead and list it up here, we need to collect like terms and put this in standard form. In standard form, we need to have the largest exponent first, so I'm going to start with a cubed, and I'll list that first. Then the next largest exponent is going to be x squared, and I have 2 of those. So let's consider what negative 3a squared plus negative 5a squared would come out to be. That's a negative 8a squared. Then following that, I need a to the first power. These 2 items have a to the first power. Let's go ahead and combine them. That makes a positive 17a. And lastly, we have negative 6 as our last term. And this is the result of the product of these 2 numbers. A cubed minus 8a squared plus 17a minus 6. Let's show another example here. This time it's a trinomial times another trinomial. Along the top row, we'll list x squared, 3x, and negative 5. And along the first column, we'll list x squared minus x and a positive 1. And we'll finish building the table here. X squared times x squared is x to the 4th. x squared times 3x is 3x to the third. X squared times negative 5 is negative 5x squared. For the second row, negative x times x squared is negative x to the third power. Negative 3x squared is the next result, and positive 5x is the third result. Negative x times negative 5 is positive 5x. For the last row, we have 1 times x squared, 1 times 3x, 1 times negative 5. We have the table complete. Now let's collect our like terms and write in standard form. Our first entry, x to the fourth, leads the polynomial. Then we have a pair of terms that can combine. 3x cubed minus x cubed is positive 2x cubed. Then we have three terms here that can combine together. Negative 5x squared minus 3x squared is negative 8x squared. Plus x squared is negative 7x squared. Then we have two more terms that can combine together. 3x plus 5x is a positive 8x. And lastly, we have negative 5 at the end by itself. And the result for the product of these two trinomials is x to the fourth plus 2x cubed minus 7x squared plus 8x minus 5. And I feel that this table method really does a nice job of organizing all of our results for us, and it allows us to write these results fairly easily. Also, it's worth noting that you'll notice these patterns forming, especially if you take the time to rewrite your polynomials that you're multiplying together in standard form. When you have your polynomials in standard form and you multiply in this table, you'll get these nice diagonals. Even we saw the diagonals up here as well, even though our problems weren't written in standard form. But these diagonals will show up indicating like terms that should be combined together. So we'll practice a couple of those in class tomorrow. Now with this last example, I want to show you a real-world application of this sort of multiplication. In the world of business, sometimes it's very important for a company to determine the total cost of producing the number of goods that they sell. So let's say we're talking about a tire company and we're trying to figure out how much they spend in order to produce their product. Well, the calculation to find their total cost is actually relatively easy. All we need to do is multiply the number of units that they produce by the cost for each unit. Now, if we label that using function notation, we would say that total cost, T of x, is equal to whatever formula is necessary to determine the number of units that they build, and whatever formula is necessary to determine the cost per unit. Because if you think about it, the number of units that a company sells can go up or go down from week to week, whether they're at a busy time in their business or whether they're slow. And as far as the cost goes, that can go up and down either, depending on what their materials cost or whether they're being very efficient in their construction or not. And so large companies often employ mathematicians or other financial experts to determine these calculations for them. And what we have here is a N calculation, or the number of units calculation. So we can determine how many units they build in a given week. And we can determine the cost, what the cost to build those units would be. When I multiply the N for the number of units and the C formula for the cost of each of those units, that will give me the result for the total cost to construct units or construct these objects at a particular business. So let's go ahead and multiply those together. 0.02 x squared, 0.2 x, and 3 will be listed along the top row. And along the column, we have negative 0.002 x squared, negative 0.1x, and a positive 2. Finish building this table, and then we'll consider the calculations that go into each. Using a calculator off screen, I'm using a handheld here. I'll go ahead and calculate this first row. Negative 0.002 x squared times 0.02 x squared is a negative 0.000, one more 0, x to the fourth, and negative 0.00004 x to the third power. Oops, I forgot my 4 over here. And for this last one, negative 0.006. And in this next row, a negative 0.1 times 0.02 x squared is a negative 0.002 x cubed. For the second product, we get a negative 0.02 x squared. For the last product, we have negative 0.3 x. I forgot my x squared up here. X squared times nothing leaves me with an x squared. And in this final row, we have 2 times 0.02. So that's 0.04x squared, 0.4x, and 6 as my last entry. What you'll see here is that we have like terms in this diagonal and in this diagonal, and then again in that diagonal. So when we combine those like terms, we can find the total cost, and I'll list that up here. The total cost can be calculated by using this formula, negative 0.0004x to the fourth minus 0.0024x cubed. I got that result by adding together these two like terms, plus 0.014x squared. I got that term by multiplying this, by adding those like terms, plus 0.1x plus 6. So a very odd looking equation with lots of decimals, lots of zeros here, but it is a real world example. Employees or CEOs of a large company will utilize calculations like this to help determine the total cost to produce a certain number of goods. That'll help them to decide whether or not they should increase production or decrease production to maximize their profits. Now, we won't be using extremely difficult equations or equations with this many decimals very often, but I thought it was important to show you what those might look like as we move forward in this section of the class. So if you have any questions with regards to this new technique, this table technique that we practiced for these last 3 calculations, please be prepared to ask those in class tomorrow, and I'll be sure to help you understand that method. That's something that we'll be using as we move forward.